In my second video, I want to show you how the binomial theorem applies to expanding polynomials. And again, this is something that won't directly affect anything that we're doing in this class, but if you're taking an Algebra 2 class or a pre-calc class, this can be really useful. The first thing I want to look at here, the reason this is called the binomial theorem is it's used for expanding binomials. A binomial has two terms either being added or subtracted. So for example, let's say my original binomial is x plus y. If you take anything to the 0 power, that's just equal to 1. Of course, if you take something to the first power, it just gives you itself back. If you take something to the second power, you're squaring it, essentially turns into a FOIL problem, and you end up getting x squared plus 2xy plus y squared. If you take something to the third power, you're going to have to trust me here, but you could work this out, do a FOIL problem, x plus y quantity times the quantity x plus y, take that result, multiply it by another quantity x plus y. That's going to equal x to the third plus 3x squared y plus 3xy squared plus y cubed, and so on and so forth. I want you to observe a pattern that you can see here, and specifically what you want to be looking for are the coefficients of the values in these different expansions. Okay, here's the 0 level coefficient, or the constant in this case is just 1. Notice that we have a coefficient of 1 here, coefficient of 1 here. I have a coefficient of 1 here, coefficient of 2, coefficient of 1, coefficient of 1, 3, 3, 1. If you look at that very carefully, you may pick up on something that you've seen somewhere else. You see, what's actually showing up here is Pascal's triangle. If you're familiar with Pascal's triangle, it starts out 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Notice 1 and 1 add up to 2, 1 and 2 add up to 3, 1 and 3 add up to 4, 3 and 3 add up to 6, 3 and 1 add up to 4, and so on. So for example, if I wanted to expand and figure out what x plus y to the 4th power is, I can do that, continuing the pattern. These will be the coefficients of the expansion. If you look at the original, you'll notice a pattern with the two different terms that were in the original binomial. You'll notice that the x power starts out being the highest power possible, and then it drops from x to the second to x to the first. Then you'll notice there's no x here. That's really an x to the 0. So I have x to the second, x to the first, x to the 0. Notice the y exponents are the reverse. I have a y to the 0, just 1, doesn't show up here. I have a y to the first, and I have a y to the second. You'll notice this pattern continues to the 3rd power. When I take it to the 3rd power, I start out with an x to the 3rd, drops to an x to the 2nd, drops to an x to the 1st, and drops to an x to the 0. Meanwhile, the y's go the opposite direction. You have a y to the 3rd, y to the 2nd, y to the 1st, y to the 0. So one term increases in power while the other decreases in power, going basically from the highest power that is the power that you're taking your original binomial to in the first place. So for example, if I wanted to figure out what x plus y to the 4th power was, not very difficult. I know my coefficients are going to be this, and that tells me the number of terms. So I know I'm going to have a 1 x to the 4th, and I won't have a y this time. By the way, notice that like this is the 2nd power, the the exponents of the x and the y always add up to this value. So the y's exponent here is 0, the x is 2, that adds up to 2. The x and y's exponents add up to 2. The x and y exponents add up to 2. They always add to 3 on this line, and so on. So My coefficients are going to be this line here. So this is my 0 power, first, second, third, fourth power. That's my fourth power line. So I'm going to have 1x to the fourth plus 4. The x will drop by 1 power. The y will rise by 1 power. Okay? Plus, I have a 6 here as my next coefficient. I'm going to have an x dropping powers, drops down to an x to the second. My y's are increasing. That'll be a y squared. Notice my two exponents add up to 4. Plus, I have an exponent, coefficient of 4. X will drop down to the first power, 4, 3, 2, 1. Y will raise to the third power, and then my last coefficient is going to be 1, which usually I don't write there. You just write that as a y to the fourth. So there are no x's left, and now I have a y to the fourth. And that saves you from having to go through constant FOIL processes trying to expand this thing. Okay? Now, this can get relatively complicated because a lot of times you're not just going to have variables, you're going to have numbers, and there's a lot of simplifying that can happen. So for example, what you're probably a little bit more likely to see is, let me do an expansion of a fourth power of something that has a number in it. Let's say I've got something like x minus 2 raised to the fourth power. First of all, I would rewrite that as a sum. I would write that as x plus a negative 2 raised to the fourth power. And it's the same kind of thing. These are going to be your coefficients. And so you have 1 times this to the fourth plus 4 times x to the third. And it's no longer a y over here. It's a negative 2, but I do the same thing with it. So it's going to be times negative 2 plus, I have a 6, okay? It's going to be x squared. I have negative 2 to the 0, negative 2 to the first. Now I'm going to have negative 2 to the second power plus 4, and that's going to be an x to the first and a negative 2 to the third. Plus, and then my last coefficient is going to be 1 times my negative 2 raised to the fourth power. And then you've got a bunch of simplifying this time that you don't normally have. So it's going to be an x to the fourth plus, negative 2 times 4 is negative 8. So that's minus 8x cubed plus, that's going to be 4. So that's 24x squared plus, that's negative 8 times 4 is negative 32. X, and then finally that'll be a plus 16. Notice that the signs alternate in this case because I had that negative sign in the original. So a lot of times you're not going to quite see this pattern of, I don't have that y exponent in there anymore when I expand everything out. So a lot of times you'll see things that look a lot more like this. But that's the basic idea. So you look at this and you say, what does that have to do with the probability problem that I was talking about originally? This seems to have no connection whatsoever. And there actually is a connection to the example that I gave you before. If I go back to Pascal's triangle, remember that I used combinations back in my example of probability. The interesting thing happens. Remember we called this the 0 row. If I take the combination of 0 taken 0 at a time, if I have nothing, how many ways can I choose nothing? I can do that one way. Okay? Row 1. I could have the combination of 1 taken 0 at a time, or I could have the combination of 1 taken 1 at a time. I could, so go on to row 2. I could have combination of 2 taken 0 at a time, combination of 2 taken 1 at a time, or the combination of 2 taken 2 at a time. If I go down here, I could have row 0, row 1, row 2, row 3. I could have 3 taken 0 at a time, 3 taken 1 at a time, 3 taken 2 at a time, or 3 taken 3 at a time. You say, what does this have to do with anything? Check it out. 0 taken 0 at a time is equal to 1. 1 taken 0 at a time is equal to 1. 1 taken 1 at a time is equal to 1. 2 taken 0 at a time is 1. 2 taken 1 at a time is 2. 2 taken 2 at a time, 1. Okay, 3 taken 0 at a time, 3 taken 1 at a time, 3 taken 2 at a time, 3 taken 3 at a time. So, depending on the situation you're in, it may be easier to just draw Pascal's triangle in the first place. And going back to the original probability problem, for example, if I was doing 3 repetitions and I wanted to see how many times, what the probability was that I could be successful twice, I could just go into, I could just take 3 taken 2 at a time, or I could go over to that third position. This is 0, 1, 2, and I could use that value of 6 there in Pascal's triangle. Either way is fine. A lot of times when I'm doing the probability problems, I like to use the combinations because the numbers are a little bit bigger and I don't want to write out that much of Pascal's triangle. A lot of times when I'm doing the expansions, the numbers are a little bit smaller because they don't usually ask you to expand something taken to, say, the 8th power, and a lot of times I'll use Pascal's triangle instead. The point here is they're both the same thing. You can use either one you want to. So that is the background of why the binomial theorem is called the background. That's the background of why the binomial theorem is called the binomial theorem. And of course, in the previous video, you saw how the binomial theorem applied to binomial distributions in probability.